Hello everyone, this is another installment of Math 101. This time I'm going to talk to you about irrational numbers. So in previous we have been talking about rational numbers, which are fractions. A and B are integers. Remember, that's the blackboard bold abbreviation for integers. It's supposed to be a Z, letter Z, which has got this stylistic double downstroke there. Anyway, those are integers, meaning positive and negative counting numbers, and B is not 0. All right, so that's rational numbers. And early mathematicians thought that all numbers were rational numbers. And the way they thought of numbers was as lengths um, of lines. It doesn't look very straight, but you're supposed to imagine a straight line there, and the length of that line is a number. They thought all numbers were rational numbers, could be represented as fractions somehow. And that actually turned out not to be the case. So there are irrational numbers. They're harder to represent, but not too hard for us, I don't think. So we're going to take a look at some examples of irrational numbers and take a look at how they can be applied in practice. So it's unknown when the first examples of irrational numbers were devised. It probably was due to the Pythagoreans. Who were a cult of people who, I guess you could say, they sort of worshipped numbers. They were led by Pythagoras, who is also known as for the Pythagorean theorem, or the Pythagoreans are. It's actually unknown whether Pythagoras was actually a real person or not. So there's a whole bunch of mystery around this cult. They were quite secretive, so to this day we don't know the truth about many aspects of the Pythagorean cult. But anyway, they did do some good mathematics, and those are the earliest examples of irrational numbers that we have. So in order for us to make sense of this first example, we're going to have to think about the Euclidean algorithm, only this time in terms of lengths. So we've been doing the Euclidean algorithm for numbers, but it can be done for lengths too. So here I'm going to divide this longer length by the shorter length, and it fits in 2 times, and then there's a remainder here, whatever that is. So this is how we do Euclidean algorithm for 2 lengths. We define the greatest common divisor of 2 lengths. We fit the smaller one into the larger one as many times as we can. And then there's going to be a little leftover chunk, and that is going to be the remainder. Right, so that corresponds, you should realize that does correspond to the notion of division as we've been exploring it. It's just a geometric presentation of that. And given any 2 lengths, I can do this process. I can always find the remainder, and I can repeat that process over and over again. So here, I'm now going to take my shorter length, and I'm going to replace the longer length by the remainder, and now I've got a similar question, but with smaller lengths. And I just do this over and over again until I find a length that fits in both original line segments. And that is the geometric GCD. So this is something that should be, it's got a direct analogy to what we do with numbers, but we're doing it with lengths. So the Pythagoreans knew this. In fact, this is probably how they thought of Euclidean algorithm in terms of operations on lengths instead of operations on numbers. So how does this now give us irrational numbers? Well, there was a member of the Pythagorean cult. His name was Hippasus, and Hippasus is probably one of the best mathematicians in the Pythagorean cult. Not much is known about him, but a couple of interesting things that are believed is that one is that he broke his vow of secrecy to the cult in order to teach mathematics to common people, the masses. And another thing is that he discovered irrational numbers. And for one or the other of these transgressions, he was sentenced to death by the cult. He was taken out in a ship out into the Mediterranean Ocean and or Mediterranean Sea and thrown overboard from the ship, and thence perished. So that is something interesting about Hippasus. Anyway, no one is sure about how he may have first found irrational numbers, but here is a plausible explanation. So a very important figure to the Pythagoreans was the regular pentagon. And that's a five-sided figure. And it was special for numerous reasons. One is that it is the face of a dodecahedron, which is a solid that has got lots of interesting symmetry properties. Apparently the Pythagoreans also discovered the dodecahedron. I can't draw one very well, so I won't even try, but you can certainly look this up online if you're interested in it. So that's one interesting thing about it. Another interesting thing about the regular pentagon is that they would kind of describe their creed by writing it around the vertices of the pentagon. Hygeia, which means clean in Greek. Cleanliness was very important to the Pythagoreans. So, for example, they were vegetarians. Anyway, this is the pentagon. Let's just erase this letters because they're not really important for what we're going to be doing from now on. Okay, so what can we do with this pentagon? Well, we can inscribe inside it another figure, pentagram, and lots of you have probably drawn this yourself. Oops, those are all supposed to be straight lines. Everything in here is supposed to be a straight line. So that is the pentagram. And now notice that there's really two different lengths in this figure. There's the long length here, the pentagram, the diagonal, and then there's the side, the shorter length. And so with these two lengths, we can apply the Euclidean algorithm. The geometric Euclidean algorithm, and find the common measure of those two lines. Find a small measurement that fits perfectly inside both of them, so that we can say I don't know what the answer might be, but this one might be 88 little tiny millimeter sections, and this one might be 107. Where's that? 107 similar little sections. And well, I mean, we don't know, but we're just going to explore this and try to find the common measure. And because the Pythagoreans believed all numbers were rational, it would make sense that it does follow that the common measure exists. All right, so let's apply the Euclidean algorithm to this figure. That here is the longer side, here is the shorter side. Well, a little bit of geometry says that this segment here, the side of the pentagon, is equal to this segment here. And so the difference is this little chunk here. And now we do a little more geometry, and we find that this little chunk here is the same as this chunk here. Okay, so we've got one side of this inner pentagon, the diagonal of this inner pentagon is one of our differences. And if you chase things around a little more, I'm not going to go into all the detail, you can also construct the side of this inner pentagon as also one of the differences. So what we've taken is this original problem where we're trying to find the GCD of these two lengths here in the big pentagon, and it turns out that they are equal to the GCD of these two lengths in the smaller pentagon. So let's highlight the smaller pentagon. It looks like this, and there's, all these diagonals are the same because of this little symmetry that's involved, and there. So the GCD of the bigger pair is the GCD of the smaller pair. Well, we apply exactly the same reasoning, and guess what? There's another smaller pentagon nested in here, and so on. And so dot, dot, dot. We keep doing it every time we get smaller and smaller pentagons, but it doesn't change anything else. It's only changing the size of the pentagons. And what Hippasus realized is that we are in something called an infinite descent. And an infinite descent is a huge problem. It means that the Euclidean algorithm doesn't stop. So it's not really an algorithm. It doesn't stop. So what that means is, the next logical conclusion is there is no common measure. So if there was, the Euclidean algorithm would have found it. The Euclidean algorithm didn't find it, so there isn't a common measure. And that means that the ratio, which we'll talk about later, but it should be a familiar concept to you. The fraction, anyway, that is the two lengths, one divided by the other, is not a rational number. So this shows the existence of irrational numbers. It's a very clever argument. It's beautiful. I love this argument, and that's why I'm showing it to you now. So the key idea here, infinite descent. So really this is just putting together things that we know already from our Euclidean algorithm. We know that from our GCD and LCM section, and putting together a few other things here, just logic essentially and a bit of geometry. It's all really easy stuff that I think basically is doable at the high school level, and we can demonstrate the existence of irrational numbers this way. So there is some evidence that this may have been the first argument that the Pythagoreans used, but it certainly wasn't the most popular argument in the future. So the most popular argument goes more like this. So we take a square here like this, and we find the diagonal of the square. And the square we're going to say is a unit square, 1 and 1. There's something called the Pythagorean theorem, which some of you may know, and that's that if I have a triangle, it's a right triangle, so a right angle here, just like I have here. A right triangle on this side is A, and this side is B, then on this side is C. The relationship between the three sides is A squared plus B squared equals C squared. So that's something else that's in the grade school curriculum. You may remember it from grade school. So I can figure out what this length is, this hypotenuse, this diagonal, just given these two legs, A and B. So here I can figure out that this is, this is 1 and this is 1, so this one has to be, the square of this side is 2, which means that the side is the square root of 2. And the square root of 2 is irrational. Now we can do this without too much geometry, which is one of the reasons why it's usually presented as the solution for, or method for proving existence of irrational numbers, even in grade school. So we do this by saying, okay, if it is, let's assume it is a rational number. Then what happens? Well, we have this equation that root 2 is a rational number. It's the quotient of a divided by b. And we square both sides, so 2 is a squared over b squared. And so 2b squared is equal to a squared. All right. Now we're actually got ourselves a bit of a problem. So what we're going to do is assume that this is actually in lowest terms. That means that the GCD of A and B is 1, so no common factor is another way of writing this. All right. So here what we've got is this relationship between A and B. Now if A can't be odd, because if A is odd, that means a squared is odd. And think about that. 1 squared is 1, and 2 squared is 4, and 3 squared is 9, and 4 squared is 16, and 5 squared is 25, and so on. Whenever we have an odd number, we have an odd number in both places. So a number and its square are both either odd or either both odd or both even. All right, so if A is odd, then A squared is odd. That's impossible, because A squared equals 2B squared is even. And now so we have to say that A is even. So that means A is equal to 2 times, let's use another letter of the alphabet, 2D. D is some other number. So A squared is 2D squared is 4D squared. So that means that 2B squared is equal to 4D squared. And we have a common factor of 2. We're going to factor that out. And this tells us that, therefore, B is also even. And that's also impossible, because we have A is even, B is even, and both of them are even, but we wrote this as a fraction in the lowest term so that there's no common factor. So that's just it. We're done. We have contradictions all different ways. So our original assumption must be incorrect. This is not a rational number. So you can try this. Try it also yourself. Show that root 3 is not rational. And then once you've got that, you can show that root 5 is not rational. And you could pick most other numbers that aren't perfect squares. If you take the square root, it's not rational, and you should be able to find an argument in each case. It'll be just a variation on the argument that I just gave. All right, so that is the usual standard proof that irrational numbers exist. So the square root of 2 is the first irrational number, but there turn out to be many different irrational numbers. So root 3, root 5, but there are just hordes of them. There are an awful lot of them. They're certainly much more common in some sense than rational numbers. It's just that they're not commonly used by human beings, but in nature they exist and are very common. So, that's just a quick overview of some of the ideas of rational numbers. Now, irrational numbers are they seem less nice somehow than rational numbers. Rational numbers we have a lot of control over. It's easy to express them as fractions. It's easy to add them and do all the arithmetic and so on. Irrational numbers, it's much harder to do arithmetic. So, excuse me. So we have we wonder whether there may be applications of irrational numbers, and I want to show you that they are actually really important. So there's the historical importance, and it was so important that it got Hippasus murdered. But there, aside from the historical importance of it, there are some applications of irrational numbers which we commonly use. So let's take a look at one of the first and most interesting examples of irrational numbers, and that is in music. So in music, we have a 12-tone scale. This is standard Western music, I guess, European-derived music. We have this 12-tone scale, and so it's almost unavoidable. You turn on the radio, 12-tone scale. You go to the symphony, 12-tone scale. You plunk away to piano, 12-tone scale. Guitars have the frets built on a 12-tone scale, and you can see it on a guitar. You count the number of frets from one end of the guitar to the middle of the guitar. You're going to get 12 frets. So it's all over the place in our music. What does it mean? Well, it means that if we want to go from C to C on a scale, it's a C major scale, we're going to go from whatever this is. It's got a frequency in hertz. I don't know what C's frequency is. I'll have to learn that, but I know the A frequency. Let's go an A scale. So A scale is 440 hertz. That's the frequency of the scale if you measure it with an instrument, with not a musical instrument, I mean with a scientific instrument. And then we're going to go up to the next A up, and we double the frequency there. So A 440 to A 880 is what we call an octave. And that actually has something to do with the word number 8. That's Latin for related to 8, but let's just ignore the 8-ness of it. What I'm talking about here is semitones. How many semitones in a scale? There are 12 semitones in a scale, so we can go up by part of a whole tone. I'm not really good at explaining music theory, so the best way to do this is just to maybe go to a website or plunk it out on a piano if you have one available. You probably have one available on your iPhone if you want, and you just you plunk them in order, and you'll hear what all the semitones sound like. And there's 12 of them between A and A. And for a long time I wondered if there's a good reason for this. And it's not, something about nature in general. It does go back to the Pythagoreans, though, again. Pythagoreans like to play chords. Let's say a chord is 2 or more notes played simultaneously. And they found that the pleasing chords, pleasing sounds, have rational numbers. Rational ratios between the frequencies. So one simple example is that if I play an A440 and an A880, they sound nice together because the ratio is 2. This is twice as large. But I could find other ratios that sound nice with an A440 note by finding other other notes that have a rational quotient if I divide their frequencies. And the Pythagoreans were probably the first to discover that. I guess there's a history that Pythagoras was listening to a blacksmith pounding away on some pieces of metal, and noticed that sometimes the sounds were pleasing and sometimes they weren't, and found out that they were pleasing sounds when the ratios of the pieces of metal were rational numbers. So that is related to how we develop our musical scale. 12 semitones. Why 12? Well, if I divide this by 12, I'm going to divide it, and I'm dividing it not evenly into 12 parts. That doesn't sound right either. What we have to do is divide it by the 12th root of 2. So when I'm talking about ratios, I'm talking about multiplication and division, not about addition and subtraction. So if I go up one semitone, I go up by the 12th root of 2, and I go up 2 semitones, I go up by another 12th root of 2, and so on. And then I do that 12 times, and I'm going to get 2 if I multiply the 12th root of 2 12 times. That's the 12th power of the 12th root of 2 is just 2. So that gives us the spacing. If we have 12 semitones, they have to be spaced out like that. When we do that, we find that some of these combinations, so 12th root of 2, maybe, I don't know, the third one, and maybe the fifth one, sound okay. They don't sound quite as good as rational numbers do, but they sound pretty good. And so we can build our scale like this, and then that means that if I pick two numbers from the scale, an A, and then whatever this is here, they may sound pretty good together. And that is the Pythagoreans. We would say that these are close to rational numbers. So they're not rational, but they're close to rational. So that's a quick overview of why we use a 12-tone scale, because some of these powers of the 12th root of 2 are close to rational numbers. The 12-tone scale is actually better than most other numbers. We could choose numbers like, we could choose any number. We could choose 11-tone scale. We could choose a 15-tone scale, an 18-tone scale. And out of all those choices, for some reason, it's kind of a coincidence, but the 12-tone scale sounds the best out of all of them. But that's for small numbers. We can vary this, though. We can go up to larger scales, and so we can look at the 31st root of 2, 31 notes. And that one actually sounds possibly better than the 12-tone scale. It's more complicated to make it accurately, so maybe that's one reason why it wasn't done. But it was investigated by musicologists, and this is under the general heading of something called microtonal music, which I'm kind of interested in. We could change the scale from a 12-tone scale to a 31-tone scale, 31st root of 2. And I've given you some examples of what that sounds like. So there was a Renaissance composer named Vicentino, who who researched this 31 tone scale, and he wrote some pieces of music in the scale. He also had students who learned to sing in his scale so they could perform his pieces. And it was hard to find instruments to play them, or impossible to find instruments, so he relied on the human voice. His students came to hate him, and when he died, they just gave up completely on his system because nobody else used it. It was a very unstandard system. But a musicologist at, I believe, McGill University, somewhere in Canada anyway, has brought this 31-tone microtonal music back. And it's really hard to train people to sing in this scale. So what he had to do in the end was get them to sing in the 12-tone scale and remapped it using auto-tune. So auto-tune is a process that will change the note at which a singer sings using software. And some pop singers actually use this. I've heard a song by Cher, for example, and Taylor Swift is rumored to also use auto-tune. So anyway, this musicologist, whose name I'm forgetting right now, it's in the notes on the course, he used auto-tune to correct. So he got his singers to sing in a 12-tone scale and then used auto-tune to correct them to match Vicentino's music. And there are, I think, 4 or 5 pieces linked through the website. So you follow the link on the website to the article about Vicentino's music, and then you can search through it. You can scroll down to find clickable samples of his music. And I think it's mind-blowing. It's just incredible. It's so different, but it's really kind of beautiful. So something I recommend you do, especially if you're interested in music, is take a look at or listen to the 31-tone microtonal music. All right, so that is one application of irrational numbers in the study of microtonal music or alternative music structures that are used throughout the world. So 5-tone is used in Asia, and 31-tone Vicentino, and there are other examples of different scales that people around the world use. I want to give one more example of an application of irrational numbers. This one is, I again love this example. It's about paper. A little more prosaic than the music examples we were looking at before, but paper. So in North America, that is including Canada, the United States, and Mexico, we end up using 8.5 inch by 11 inch paper. And it's actually kind of arbitrary. Why were these numbers decided upon? I don't know what the answer is, but other similar numbers could have served just as well. Whereas most of the world, all the rest of the world, uses something called A-series paper. Oops, A-series. So A4 is a typical example of A-series paper. And its measurements are different from these, and its measurements are given in millimeters. So, and I'm not going to write them down. You can easily look that up on the website, on the YourCourses site. But there is a critical difference between these two. And that's that if I take an 8.5 by 11 sheet of paper and I cut it in half, and we would do that if we do 2 up on a photocopier, say. We want to take 2 pages and put them on one. I do this all the time so that documents can fit into my little carry portfolio. So I have a hole punch, a special hole punch, and I put and I copy things so that they're 2 up. and they fit perfectly in my portfolio. So the problem with this is that we end up changing the aspect ratio. We end up changing the aspect ratio of the paper, so it's actually a different shape when it's 2 up. So this piece of paper here, this chunk, has a different shape from the original. And so that causes problems with margins. If I'm going to print something 2 up, I have to print stuff. I have to be very careful about the margins, because if I try to use too much of the paper, one margin will go over, and if I fit it inside, then I end up with bigger margins on one edge. So this is kind of unfortunate. Now you may wonder, well, is this true? This seems like it might be something that's true for any piece of paper, any way I design paper. It turns out that it is not. It is not the same. There is one choice which doesn't have this problem, where the 2 up is exactly the same shape as the original paper, and that's A4 paper and A5 paper. So A5 would be the smaller one, and A4 would be the bigger one. And A5 and A4 paper are exactly the same size. How can we do this? How can we design the paper? Well, it turns out we have to use irrational numbers again. We have to use the square root of 2 in the 2 as one of the sides of the paper. And there are other considerations. So I'm not going to go into great detail about it. You can read up on it in the website, but that is the general idea that a series paper does not have this problem with the aspect ratio. The 2 shapes are different. All shapes are exactly the same. In fact, I can even subdivide it. So here I've subdivided it, and this is the same shape as the original. This is the same shape. This is the same shape, this is the same shape. So it has this beautiful property, and you can see there's a diagram that I've included on the website that illustrates this. All right, so those are 2 examples of how we can benefit from the use and understanding of irrational numbers. Of course, there are many others. Those are just 2 that I wanted to select. So I just wanted to give you a kind of an idea about irrational numbers, a general overview, and I think that's it now for this section of the course. Let's move on. After this, we're going to start talking about ratios next. All right, so